Hi, everybody. It's Professor Mitchell, continuing with Chapter 5. Today, we're looking at Section 5.2 on polynomial functions and adding and subtracting polynomials. In this section, we will define polynomial, monomial, binomial, trinomial, and degree. We'll define polynomial functions. We'll simplify a polynomial by combining like terms. And finally, we'll add and subtract polynomials. And throughout this chapter, we're working on SLOA, performing mathematical operations on algebraic expressions. All right, so we start with a little bit of vocabulary. When we talk about a term, we're talking about a number or a product of a number and variables raised to powers. The coefficient is the numerical factor of a term. A constant is a term which is only a number. It has no variable part to it. And finally, a polynomial is a sum of terms involving variables raised to whole number exponents with no variables appearing in any denominator. All right, so here's an example of a polynomial, 7x to the fifth plus x squared y squared minus 4xy plus 7. This polynomial has four terms, which are 7x to the fifth, x squared y squared, negative 4xy, and 7. So notice that any term that has a minus in front of it, we think of that term as starting with a negative. The coefficient of each of these terms in the order they're given are 7, 1, negative 4, and 7. So remember that for x squared y squared, there is an invisible 1 right here. So that's how we get the coefficient of 1. This 7 at the end is a constant term because it has no variable part. All right, so that brings us to types of polynomials. A monomial is a polynomial with only one term. Notice the prefix mono. Binomial is a polynomial with two terms. And trinomial is a polynomial with three terms. All right, any polynomial that has more than three terms generally doesn't go by a special name. There is such a thing as a quadrinomial, but nobody uses that term anymore. Polynomial, even though the prefix poly in English means many, a polynomial does not have to have many terms. It just has to have at least one. All right, that brings us to the degree of a term. To find the degree of a term, you take the sum of the exponents on the variables contained in the term. The degree of a constant is 0. Remember, a constant has no variable part. All right, so if you had the term 5a to the fourth, b to the third, c, the degree of that term would be 8 because 4 plus 3 plus 1 equals 8. Remember that c can be written as c to the power 1. All right, and then the degree of a polynomial. To find the degree of a polynomial, you find the degree of each term and then take the largest one of those degrees. All right, so for example, the degree of the polynomial 9x to the third minus 4x squared plus 7 is 3. Because the degree of each term is 3, 2, and 0. And the largest number in that group is 3. What is the degree of the polynomial we looked at earlier? 7x to the fifth plus x squared y squared minus 4xy plus 7. Well, that polynomial has degree 5. Because the degrees have, the terms have degrees 5, 4, 2, and 0. and the largest number in that group is 5. Please be aware that even though in these two examples, the first term happened to determine the degree, it's not always like that. Okay, so if I had just switched this to 9x squared minus 4x cubed plus 7, the degree of that polynomial would still be 3. So it goes by the term with the largest degree, not necessarily the term that comes first. All right, so finally, example where we're going to put pencil to paper here. So let me switch over to my tablet. All right, so this time we are given a polynomial function, p of x equals 3x squared minus 2x minus 5. So we've looked at functions before. I think up until now, the functions have been linear. So what I'm going to recommend is that you write the function replacing the variable with just a set of blank parentheses. So 3 blank squared minus 2 blank minus 5. And then fill in the blank with whatever the number is, in this case 1. And then just use your order of operations to simplify that expression. So 1 squared is 1, 3 times 1 is 3, 2 times 1 is 2. So we have 3 minus 2 is 1, 1 minus 5 is -4. All right, now be careful in letter B. We're looking for P at -2. And as usual, at any time, please feel free to pause the video, try the problem yourself, and then come back and compare notes. So I'm going to do the same thing that I did in letter A. 3 blank squared minus 2 blank minus 5. And this time in the blank, I'm going to put a -2. Okay, now here's why I needed to be careful. I think it was just in the last section, we talked about the difference between the opposite of the square of 2 and the square of opposite 2, right? Those come out to two different things. So in the case of letter B, I mean the second one, the square of -2 is 4, +4. And then -2 times -2 is +4. So we have 12 plus 4 is 16. 16 minus 5 is 11. All right, let's go back to the presentation. Let's see. So next we have combining like terms. When we talk about like terms, we're talking about terms that contain exactly the same variables raised to exactly the same powers. And now that I think about it, I think we talked about some of this stuff at the beginning of chapter 2. I seem to remember going over some like terms there. All right, so for example, if we wanted to simplify these two polynomials by combining like terms, we can do that. Let's go back to the tablet. All right, so we'll start with 7.6y plus 3.2y squared minus 8y minus 2.7y squared. So what I'm going to do is, well, I don't think we really need to write the like terms next to each other. We can just recognize that 7.6y and minus 8y are like terms. And if we do the operation on those coefficients, 7.6 minus 8 is -0.4. So that gives us -0.4y. And then I'll do the same thing with the y squared terms. We have 3.2y squared minus 2.7y. And that's going to give us plus 0.5y squared. And that right there is a perfectly good answer. I've noticed that sometimes when students come to me, they've already come in the habit of writing the terms in descending order of powers, which will be useful for something that we're doing later. So I'll just point out that you could either leave it like that, or if you want to, you could reorder the terms. Just be sure to keep the minus sign on the negative 0.4y. So either one of those would be a good answer. Okay, now we come to this thing. All right, don't panic. 1/6 x to the fourth minus 1/7 x squared plus 5 minus 1/2 x to the fourth minus 3/7 x squared plus 1/3. So I see three pairs of like terms. I see one-sixth x to the fourth minus 1/2 x to the fourth. I see negative 1/7 x squared minus 3/7 x squared. And then finally, I see 5 plus 1/3. Okay, so I guess I should go ahead and just write those next to each other. 1/6 x to the fourth minus 1/2 x to the fourth. You know what? I'm going to do it like this. And then on the next line, minus 1/7 x squared minus 3/7 x squared. And finally, plus 5 plus 1/3. Okay, the reason I decide to write it like that for now is that I am going to have to get some common denominators. For example, in the first pair of terms, the common denominator there will be 6, right? So I will multiply this term by 3 over 3. The second pair doesn't need a common denominator. It already has one. And then in the last pair of terms, I'm going to think of this as 5 over 1, and I'm going to multiply the top and the bottom of this by 3 over 3. Okay, so in the first pair, we have 1/6 x to the fourth minus, think about what this gives you, minus 3/6 x to the fourth. So 1/6 x to the fourth minus 3/6 x to the fourth is negative 2/6 x to the fourth, and I will simplify that. Negative 1/7 x squared minus 3/7 x squared is minus 4/7 x squared. And now 5 over 1 times 3 over 3, I'm going to think of that as 15 over 3. 15 over 3 plus 1 over 3 is 16 over 3. So this answer is almost perfect. We just need to simplify the 2/6 here. So my final answer is going to be negative 1/3 x to the fourth minus 4/7 x squared plus 16 over 3. All right, back to the presentation. I think there might be only one more example. Yes. So adding and subtracting like polynomials, it turns out, is really just combining like terms. So we're going to end with these two examples, which I have on the tablet. All right, so first example, 3x minus 8 plus 4x squared minus 3x plus 3. First of all, remember that since we are adding these two polynomials, that means the parentheses don't really do anything. So we might as well take them down. And then I'm going to look for all my like terms. 4x squared is the only x squared term, so that could kick off our answer. When I go to combine the x terms, I have 3x minus 3x, which gives you 0x, and that's why we sometimes just do this. -8 plus 3 is -5. So the sum of these two polynomials is 4x squared minus 5. And then finally, we have subtract 5y squared plus 8y plus 2 from 7y squared plus 9y minus 8. I remember telling you a long time ago that subtract from is one of my favorite kinds of problems. Do you remember the two things that you have to watch out for in a subtract from problem? Think about if it said subtract 8 from 12. Okay, first of all, it switches up the order. Subtract 8 from 12 means 12 minus 8. Subtract this polynomial from that polynomial means that polynomial minus this polynomial. So it switches up the order. And then do you remember the other thing I told you last time this came up? Well, if we're subtracting 5y squared plus 8y plus 2, we need to put that expression in parentheses, because if I leave it written like this, we are not subtracting 5y squared plus 8y plus 2. We're just subtracting 5y squared and then adding 8y and 2. So that's a different problem. Put the parentheses there. And then to get rid of the parentheses, you have to distribute a -1. So we have 7y squared plus 9y minus 8 minus 5y squared minus 8y minus 2. All right, so now combining the like terms, we get 7y squared minus 5y squared is 2y squared. We get plus 9y minus 8y, which we can just write as plus y. And then finally, we have -8 minus 2, which is -10. Okay, so when you subtract those two polynomials, you end up with 2y squared plus y minus 10. And that's going to do it for this section. We'll see you next time.